Dr. Butler, and this is AP Chemistry. Now we are going to be doing problem on page 685. We are going to be doing practice exercise number 1. I encourage you to try to figure this out and solve it. And if you can't solve it, then you can check with this video solution on how to do it. This is the question. What is the pH of a 0.40 molar solution of benzoic acid, which is p.685 and it has a Ka value of 6.3 times 10 to the negative 5. All right, so I'm going to write the equation. So we get an H plus. It's going to be this H here at the end that is going to go. So we got C6H5COO minus is the other side of that. All right, our equilibrium expression is H plus times C6H5COO minus over C6H5COOH for this. Now in this case, what we know is we know the Ka value, so we know what this is. We also know what the initial concentration of the C6H5COOH is. And that's it. We have to find the pH value, which means we have to find the H plus concentration. So that's what we need to find, and we're going to need to use an ice table to solve for this. So I'm going to set up my ice table. We have C6H5COOH. We have H pluses, and we have C6H5COO minuses. Like this. And we do an ice. Okay. So what do we know is we know the initial concentration of our benzoic acid, which is 0.4 molar. We know that our initial concentration of the other things are 0. And that's it. We don't know anything else in this table. And so we would solve it by subtracting an x. So it's 0.40 molar minus x. And adding x to the other sides. And so these values are x. But we do not know what those values are. So I'm going to get another piece of paper and put all of our equilibrium concentrations right here into our equilibrium expression, because we know what Ka is. So Ka, which is 6.3 times 10 to the negative 5, is our H plus, which is an X, times our C6H5COO6, which is an X, divided by 0.40 molar minus X. Okay. Now, there is a trick that you can use if you follow it to try this. If X is less than 5% of HA, then we can use a small x approximation. So a small x approximation is if X is less than 5% of HA, we can use a small, and we're going to assume that. We're going to double check and see if it is less than 5%. But we are going to assume it is right now because it's going to make the question a lot easier. If we use a small angle approximation, then 0.40 minus x is approximately equal to 0.40. Okay? If we're less than 5%. And so let's use that approximation and solve for Ka. Otherwise, we would have to use a quadratic formula, and it is a little bit harder. So x squared over 0.4 equals our Ka value, 6.3 times 10 to the negative 5. Like that. Solve for x squared. 0.3 times 10 to the negative 5 times 0.4. X equals the square root of all of that. And we'll put that into the calculator. which ends up being x is 0.0050 molar is what that is. Now, is that less than 5% of HA is the question. And we could check and see if x is less than that. And we do 0.0050 divided by 0.4 times 100. 0.005 divided by 0.4 times 100 is a 1.24%, 1.25%. So this works. Check, the small angle approximation works. Our x is this, so x is our H plus. So our H plus concentration, x is H plus right here, is 0.0050 molar. So we need to find pH, which is the negative log of H plus, and we plug that into our calculator, 0.0050, take the negative, I'm going to do log of negative 0.0050. Log of 0.0050 is negative 2.3, so the pH is 2.3, a negative of it. There's your answer to solving one. We use the small angle approximation to get that, small x approximation.